Okay, the time is ready. Thank you, everyone, and welcome to this webinar, Accelerate Your Plastic Product Development with Autodesk Fusion and Moldflow. My name is Martin Aronsson. I'm account manager here at NTI, and I will be the moderator of today's webinar. And if you have any questions, we will have a Q&A at the end of this webinar. And for you who are joining us for the first time, NTI is a full-service supplier of digital solutions for the construction, design, and manufacturing industries. We are Autodesk Platinum Partner, founded in 1945 and present globally in 13 countries with over 900 colleagues. And with that, I will welcome the speakers of today. Start with Mohsen Hesami, who is a Moldflow and CFD simulation application engineer based in Gothenburg, Sweden. He helps customers leverage simulation tools for better decision making in early design phases and to address downstream challenges. With over 20 years of experience, Mohsen has worked with automotive suppliers across Sweden, Germany, and Spain. His expertise also spans consumers, products, and AEC, where he provides technical support, training, and insights to improve workflows. Louis Barnes is a senior solution engineer at Autodesk based in Manchester, UK. He helps customers realize the benefits of Autodesk solutions by identifying opportunities to improve their workflows and processes. Louis has a broad experience of CIE tools and was the first Autodesk Moldflow Insight certified expert in the UK. Before Autodesk, he provided simulation services, training, and support to engineering professionals across all industries. So, thank you.
Thank you very much, Martin. So let's get started today. So the product that we're going to look at is this racing simulator steering wheel. And the back cover of the steering wheel is injection molded and illustrates many of the common challenges faced in getting a product into production. So no matter which industry, whether that's consumer electronics to automotive or medical devices, the process of development is universal. Every aspect of what you see here on the screen has been developed within the Autodesk Fusion platform. So it's a great showcase of Fusion's capabilities. And Fusion isn't just CAD, and it's not just CAM, not just simulation, documentation, rendering, or electronics. It's all of these things, provides all of those technologies in one place with the connected data set. So if we look at the product development process for a plastic part, it requires very effective collaboration between many different roles. So with Fusion, the whole team can collaborate on a connected data set to achieve a seamless development process, where if one area updates, then that change trickles down the entire process. So starting with the initial concepts in the form workspace, the designer sets out that product definition. Then the mechanical and electrical engineers worked on the detailed engineering of the product, making use of capabilities for generative design and simulation to optimize the product itself. To turn that design into reality, the manufacturing engineers used Fusion's advanced CAM functionality to program the machine tools and make the mold itself. So Mohsen's going to take us through the challenges with plastic product development and how this could be addressed in Fusion's simulation workspace.
Thank you, Louis. The injection molding process allows us to consistently manufacture high volume of quality parts at a low cost. Upfront tooling cost is high, so there is a big risk of getting it wrong. We only find out about quality issue when the first part are manufactured. By that point, it is too late to change the design without incurring high cost and delay. As you see in the picture, those challenges are from top left, voids, wet lines at the A surface or visible surface, sink marks, warpage, venting problem, burn marks at the middle, and short shot. Next, please. And as I said, you find out it in the production. When we consider the development process, we only discover these issues at the production stage. But this time, it's too late. Any changes to part or tool design will be time-consuming and costly. Using injection molding simulation at the right time encourage more efficient design and improve collaboration. Moldflow has been the technology trusted by industry to simulate the injection molding process for 46 years now. Now to the demonstration of the product. As you see, you have a plastic flick, especially for the plastic design. There you can create bosses, ribs, and so on. In Fusion, you can open all kind of CAD files, or you can start design by yourself. When you send it to the simulation package, you can do many other things than injection molding, as you say, simplify, finite elements, heat exchange, and so on. Today, we are looking at injection molding process. As I said, you can create your part, or you can bring assembly. If it's assembly, you choose your part, target body, and the other parts will be disappear or not disappear, suppressed, and you can do the simulation. And if you look at the backside, Fusion has put injection point, injection location, plastic entrance at the center of the part. You can choose material from the database. Over 14,000 commercial plastic parts is in the database. And you can sort it by the manufacturer, grades, and in this case, we choose a PCABS. And as you see, there is a description of that in the next second. You can see the description of the plastic part, plastic quality, and the process settings is there as well, which is moved to the process setting in the simulation automatically. You don't need to do that. And the injection point, maybe it's not feasible to put it at the center in that area. You can create new injection points, as you see here, and delete old one, or you can move it if you want to. When you are done, you can choose the static surfaces as well, which is visible, and the software will concentrate on that surface if you have weld lines or if you have sink marks and so on. This is the pre-settings that you need to do in order to do a simulation. Just choosing material and putting injection point. And as you see, the melt temperature is coming from database and the mold surface temperature as well. If you're happy with that, then you can pre-check your simulation, or as you see, there is a green mark in the checking. So you are good to go. Here, if I click on solve, a package will be encrypted and send it to the Autodesk cloud, and the simulation will be solved in the cloud. And when the simulation is done, the encrypted package will come back to your computer. So it's only for your eyes and no one else. It's very safe transition between your computer and the cloud and back. And I have done those simulation. We can look at the result. And as I said, the result is stored in the cloud and is coming back for you to review. Here is the overview of the simulation, and you can see the field phase, field time, and pressure. And if there is any problem, you get the warning at the bottom of that phase. Here you see you have warning in the field phase, you have warning in the packing and cooling phase, and the end part have some warnings. Let's look at the results. And as you see, the pressure is very high, 74 megapascal. Or 72.8. Viewing the result will show you where that occurs, and confidence of fill. You can see the wall is filled at the last phase. The plastic should get at the edges at the same time. You can probe that and see what the problem is. 74 is too high. And you know that the high injection pressure cause that you need high clamp force. So this is something you have to solve it in this case. Fill time 1.57 seconds, automatically calculated. And you can animate the fill phase to see fill pattern. Now you can see at the handle is heated plastic is filled, but not that part of the wall. That caused the high pressure need. And if you look at the quality, injection pressure is the pressure you need to push the plastic inside the cavity, and you should keep it below recommended. Here is 90, but 90 is very too high. I recommend you to keep it under 50 or 60 megapascal, because the runner system is not designed in that part, and you will have some lose in the pressure lose in your cavity and runner system. To lower the pressure, you can change the material, which is not recommended, but you can do 2 gates. Here is to place 2 gates at the sides. With the 1 gate, you get the weld line at the center bottom, but 2 gates will give you 2 weld lines. But later on, you can see that those weld lines has good quality, and it's not visible. It will be covered by other parts. Getting the result from the cloud. Here you are. The quality, fill confidence, the yellow warning at the bottom wall is gone now. So you can lower the pressure with 28%, having 2 gates, and only 56.6 megapascal. Remember that you don't have runner system in it. It's part only simulation. Okay. As I said, the weld lines is no issue. The back part will be covered, and you cannot see that. Looking at the quality prediction, you can see some issues. The yellow is some kind of warning. Here you can see the sink mark and the value you can choose and scale away those, sink mark which is not visible. 0.003 is visible weld lines, and it's because the volumetric shrinkage you have, and the ribs at the backside and radius is too big. So imagine that you're sitting and thinking about the ribs and the other kind of part design, and you cannot send to the tool maker all the time. You want to see, what if I change the thickness of the rib and the radius at the bottom? What happens? Can I get rid of the sink mark or not? Maybe it's the other problem. At the result, you can, I will show you two simulation at the same time. This is the one with the small rib and radius. I'm scaling away. You can see that the two gates has better result, and smaller ribs, smaller radius, the sink mark is disappeared. You don't have it anymore. Even if I change the scale to 0.02, still no sink mark. So if you find out these kind of things in the production, then it costs many time and costs. Here the comparison of the quality prediction, and those areas which is screw, you can change that, but in that case is not problem. In the filling phase, you can see that it's green, and packing and work and final part has still some warnings, and the warning comes from the work page. You can see the work page, and even the flatness. Flatness is important if two parts is coming together, assembled together, and you can see that the tolerance, you can put the tolerance. Maybe your assembly can take away, eat up those tolerances, and then there's no problem. Otherwise, you should have some action in it. You can exaggerate the magnitude of the warpage and flatness. And now Louis will show you beyond the fusion what you can do with the Moldflow technology.
Thank you so much. Thank you so much, Mohsen. So that's a really great example of what can be done within the Fusion environment to take that product from initial concept, adjust the design, adjust the gating solution to give us confidence we're going to get a good result. And hopefully it's going to meet our cost requirements. But if we think about the design phase of the plastic part, this is where a huge impact on our overall part cost exists. So 70 to 85% of the total cost of a plastic part is locked in at that design phase. And if we think about plastic part cost, it's basically the combination of raw material cost plus the tooling costs and its ongoing production cost. So early in the design process, we select the material, we decide the part thickness, and that locks in the volume of material we require for each component. The tooling costs will largely be driven by the size and complexity of the mold to be made. So steps to minimize that complexity, such as reducing the number of moving cores for undercut features, can help reduce that tooling cost and minimize the maintenance requirements as well. So in production, the time taken to cool the molten plastic is going to have a dominant influence on the overall cycle time. And that again is directly related to part wall thickness. So smart product design happens when we consider all of this manufacturing process up front from the start and can optimize the part thicknesses and materials efficiently. In terms of technology to do this, the Autodesk injection molding solutions have capabilities which span all stages of the development process. So at the product design stage, Fusion simulation extension is ideal. So the intuitive workflow that Mosen demonstrated gets us valuable design feedback very quickly. For assessing the impact of tooling, the Moldflow products allow us to include modeling the feed system of the tooling, along with any mold cooling which exists within that tool design. Moldflow Insight offers the very highest levels of precision and user control over the process. So it allows us to model in advanced processes such as compression molding, using thermoset materials, gas assist, this kind of thing. And it gives us a lot of control over the individual process for things like running a design of experiments for process optimization. So let's have a little look at what we can uncover with Moldflow with this product once it's gone through the design phase and into tooling. So firstly, we can push the data from inside Fusion, where we rejoin the study, and move that into Moldflow Insight. So once we're inside Moldflow Insight, we generate the finite element mesh, which can be done automatically. And we can import the features of the mold tool itself. So that would include the runner system, which delivers the melt material to the part. And we can also include the cooling. So here's the proposal from the tool designer, which includes a core and cavity cross drillings to try and extract the heat effectively. The first result I'd look at is this mold temperature result. And we want to make sure that this is as uniform as possible throughout the part. But immediately we can see there are a number of hotspots, particularly around this top area where we've got some deep pockets due to the ribbing. Got a significantly higher mold surface temperature in those areas because it's difficult to conduct the heat out of those regions effectively. And having those hotspots is a real risk in the process because not only will it slow down our cycle time and increase cost, but it also potentially cause distortion issues. Like we see here, looking at the warpage result, the wall there will deflect, which will create a poor quality fit between the faceplate and this back cover. So we want to try and avoid this kind of issue wherever possible. So what we really need to do here is rethink our cooling and try and improve the overall heat extraction uniformity. So let's look at a second iteration of the cooling based on this feedback. So if we look in this region, we can use Fusion to develop a mold insert. So this could be manufactured from a high conductivity material, which may be a beryllium copper alloy, which should have a much higher conductivity and extract the heat more effectively. When we look at the cooling, potentially we could add in cooling features like baffles into those pockets where there's space allows to be able to, again, get the cooling water into those areas. When we look at the temperature plot, we can see we've got much improved uniformity of temperature throughout that core region. So it's a much better starting point for optimizing our process. We know that we should be able to have an efficient molding cycle. Comparing the two results side by side again, we can see that temperature distribution is greatly improved, and we might be able to achieve something around like a 15% cycle time improvement with that improved cooling design. Zooming in on the impact on warpage, it's about a 50% reduction in deflection just by including that cooling channel, that cooling insert. So again, we've solved our cycle time and our warpage issue. We can now proceed to production and manufacturing of the mold with confidence. So in summary, we have seen that in today's competitive manufacturing world, we can't really afford to make mistakes. So when we start cutting steel to make the mold, we need to be confident that it's going to be right first time. We've seen how adopting an upfront simulation process with Autodesk Fusion allows us to identify and resolve those part quality issues and reduce the risk of costly tooling rework. As the design matures and moved into tool design and production, Moldflow adds additional insight into the process, optimizing the cooling channel placement and further opportunities to improve the process. So plastic product development is faster and more successful when we collaborate early. So don't hesitate to get in touch with the NTI team to help understand how these technologies can support your next project. So thank you very much for your attention. I'm going to hand over to the Q&A section now. We look forward to any of your questions.
Yeah, thank you, Lewis. Like you said, if you want to write questions, you can use the you can use that function, or you can just raise your hand if you want to ask vocally, and I will access your microphone, so to say. But we got two anonymous questions here during the webinar. The first one is, who should be doing the simulation? Is it the tool maker or the part designer?
Do you want to take this one, Mosen, or shall I start? If you ask me, everyone should do that, because as I said, if the designer is doing it, so can think about what if I do that, what's the impact of the final part. So designers should do that, or those who create the ideas of the part. And of course, when the designer maybe do not have knowledge about the runner system and cooling system, then the tool maker should do that. You should ask the tool maker, show you their solution. And if they can guarantee that the part is okay, then you can go on with your ideas. But as I said, starting with the idea, which is designers' work, they should do that, of course.
Yeah, completely agree with you on that, Mosen. I think when we're at that part design stage, it makes absolute sense for the engineer or product designer to be simulating, because it's easy to make rapid changes and it's not going to take weeks to get the feedback. And by that point, all of the other components of your assembly have been matured, and it completely derails your development process. An interesting one is around that question about who should be doing the later stage simulation. So obviously, toolmaker is in a good place to use that to make sure that the tool they're designing is successful. We also see a lot of Moldflow users getting a lot of value from validating that toolmaker proposal themselves. And that's a really interesting workflow, because it might be that the toolmaker has a slightly different motivation than the part designer. So maybe the toolmaker doesn't have the same, let's say, need to minimize cycle time, because they're not paying for the kind of production of that part. They're just delivering the tool itself. So it's a bit of a balance, and I think there's always a place where more information is better. So that'd be my view on it as well.
Yeah, thank you. Another question from Morgan. What's the cost per year for either the two of these?
So there are a number of different access models. I don't have the full price list, Swedish price list in front of me, but there are a number of different access models which can get into around how you'd make use of the software. So broadly speaking, both the Fusion Simulation Extension and Moldflow are available as annual subscriptions. The simulation extension is also available on a monthly basis. And the really interesting thing as well is that we've got flex access to all of these technologies. And that means that using a pool of flex tokens, which can be purchased in very small quantities, can be used on a pay-per-result basis, where you only pay for the analysis that you do. So that's an ideal solution if you've only got an occasional need for that in-depth simulation. So basically, there's a number of different options, and depending on your workflow and the number of projects that you're developing around plastic, there's a solution that will fit. Hopefully that answers it enough. Have you got anything else to add there, Martin?
Yeah, like you said, Lewis, I can come back and to you, Morgan, about the Swedish prices regarding which type of license you would prefer. We can have a separate meeting about that after this webinar. David asked, when sending out a simulation to the cloud, can we specify which country the server is based? This is regarding to design of export control parts that can't leave the country, even encrypted.
So in terms of servers for the Fusion Cloud Solve, no, you can't currently specify where that server is located. So our recommendation, if you have got an export control part where you require on-premise data control, would be to use the desktop solutions. So Moldflow Advisor and Moldflow Insight would be could be completely kind of say offline solutions where you can retain the data in one place. So we do see that is still a necessary solution in some industries and some use cases.
Yeah, sorry, it was a follow-up question here from the same participant. Follow-up question, is there any part of Moldflow that reach out to servers outside our country that we should be aware of using it?
So in terms of the overall functionality of the software, if we're solving on our own machines, no, there's no kind of data transfer going on with the Autodesk servers or any external server. Depending on our licensing method, it might just be the authentication of the license happens across the internet to make sure that you've got a valid license, but that's not transferring any kind of proprietary kind of or confidential data. So it should just be for license validation that we just communicate across the internet.
Yeah. Okay, that was all of the questions I got. Thank you, everyone. We will also send out a survey about this webinar, what you thought about it. And there you also can ask more questions if you have anyone. Thank you so much for participating. And thank you, Mårten and Luis.
A pleasure. Thank you all.
Pleasure.
Have a good day.
Have a nice day.